Well, good morning. It's 11:34 on Tuesday, the 6th of October, 2020. This is supposed to be linear algebra class, Math 237, and I think part of the reason nobody's here is when I loaded the class last night, set up the Zoom, did everything I was supposed to sort of do, I forgot to post it. I don't know why they have multiple steps there, but they do. I saved it, but I forgot to post it. So I don't know if any of you have tried to find it and couldn't find it, but it's out there now. I went out this morning to see why nobody was here at 11:30, and I saw I had forgotten to post it. So I posted it then. So it's been posted now about 5 minutes, and still nobody's here. So I don't know if y'all gave up looking or what. But because we're supposed to have class today, I'll go on and go with class, and you can pick it up on the YouTube videos, because I am recording the class at this point. Normally I'd ask if you had any questions, if there's any issues, concerns, or other things like that, but you're not here to ask that to or of. Okay, now where we are, we're in chapter 2, matrices, section 2.3, the inverse of a matrix, and we just had gotten down and found an inverse of a matrix, and I think we had finished that problem, and it said to confirm that we did indeed have an inverse matrix, we needed to confirm that it met the requirements of an inverse matrix. And what are those requirements? Of course, to be an inverse, A times the inverse of A must equal the identity matrix of the proper size. Okay, remember, A and the inverse of A have to be square matrices, and of course the identity matrix is a square matrix. Okay, and that's also A inverse times A. So we're going to confirm that what we found last time is indeed an inverse. Okay, the original matrix we were given, A, is equal to 1 minus 1, 0, (1, 0, negative 1, and negative 6, 2, and 3. Now, in the last class, last Thursday, we found the inverse of this matrix to be, or at least what we think it is, A inverse to be and I don't have my pad here, so I'm going by what they did in the book. Okay, as negative 2, negative 3, negative 1, that's a minus sign, negative 3, negative 3, negative 1, and negative 2, negative 4, and negative 1. Now that's a negative 2 there. I hope you can read that. I think what I will do, because it got a little wacko here for some reason. This is such a pain in the neck. You go to erase something and it doesn't erase. Okay. Okay. All right. So let's first do A times A inverse. Of course, a 3 by 3 by 3 by 3 is going to be a 3 by 3. So this will be A inverse will be a 3 by 3 matrix. And that would be blank, 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 blank. You don't have to do this. Sort of helps me with the bookkeeping. First row, first column would be first row of A times first column of A inverse. That would be 1 times a minus 2 is minus 2, plus 3, that would be a plus 1, plus 0, sure enough, that's a 1. The 1, 2 entry here, first column, first row, second column, first row here, second column here, will be 3 times minus 1 is minus 3, minus 1 times minus 3 is plus 3, minus 3 plus 3 is 0, plus 0 is 0. Good deal. 1, 3 entry here, first row, third column, is negative 1 times a negative 1 is a minus 1, negative 1 times a negative 1 is a plus 1, and 0 times that is 0, so negative 1 plus 1 is 0, plus 0 is 0. So far, so good. The 2, 1 entry here, second row, first column, second row here, first column there. Negative 2, or 1 times negative 2 is negative 2, plus 0, and then plus 2 is 0. Perfect. 2, 2 column here, second row, second column, 2, 2, will be second row here, second column there. Negative 3 plus 0 is going to be a negative 3, plus 4 is a plus 1. Good deal. The 2, 3 entry here, second row here, third column here would be a negative 1, 0, plus 1, that's a 0. Okay. I'm still sort of concerned nobody has shown up yet. Okay. Let me just check for a moment here. See, I don't know if you can see it. I'm going to do a new share here so you can see it in case you're looking. There is this class, Math 237, Linear Algebra, 3 posted, 3 total, and I'll show the posting here. And there it is. Ah, here's Kira. Good deal. I was beginning to worry. Okay. Kira, sorry that I botched up there. Had you tried earlier?
Yes.
Okay. What happened, I don't know how it happened. I may have done this once before in the past, but it's been a long time. I saved the post, saved the announcement, but I forgot to post it. And I found that out this morning right at 11:30 when nobody was here. And I went and checked, and sure enough, I found out I had failed to do it. So I posted it then. Let me go back to the screen sharing where I was. I've already started class where we left off last time. Okay, have you heard from the other 2 guys?
I heard from Jesus. I told him that the link on there now.
Okay, but we haven't heard from James. Okay, I couldn't remember his first name. Okay, all right. What we're doing is the problem we worked on last time, example 3 on page 65, had this as matrix A, and I think in class we calculated and got this as matrix A inverse. Now for some reason it took off part of my equal sign here, and I can't find the key. There it is. Okay. It just every now and then removes a mark. Okay. And now what I'm doing is doing A times A inverse. If this is indeed the inverse of A, then the product of those two should be the identity matrix. And so far so good. We're down to the point of third row, first column. So third row of A times the first column of A inverse would be -6 times -2. That would be a positive 12, minus 6, 2 times -3 is minus 6, would be a positive 6, and then another minus 6 from 3 times -2, that adds to 0. Fantastic. And here is Jesus coming in now. Okay, and we still haven't heard from James. Jesus, have you heard from James?
No, sir.
Okay, sorry about that. I was explaining to Kira that last evening, it was probably not that late in the evening either, mid-afternoon, when I had finished my 3:45, 4 o'clock class, whatever. I usually then send out the invites for the next day. I did everything, I saved it and everything, but I guess I forgot to post it. I think I hit the key, but then just went on, and evidently it didn't catch, because I always, knock on wood, post, and for some reason it didn't catch, and I didn't notice it until this morning when no one was here at 11:30. Always when no one's here, I go out and check, and sure enough, it was, however they said it, it was there but not posted. So I went in and posted it at 11:30, and I'm glad y'all made it, and hopefully James has not given up. All right, what we're doing here, if you remember last time, they gave us matrix A here, and we were to find the inverse of A, which we did and found this amount. And then I said, y'all want to check this yourself, or you want me to check it in class? You said, check it in class. So here we're doing it. We're multiplying these two together to see if we get the identity matrix, and so far so good. We're on the 3-2 entry now. Third row, second column, so let's do third row here times second column here. -6 times -3 is positive 18, minus or plus a 2 times a -3, that would be a -6, so that would give us a positive 12. Positive 18 minus 6 is positive 12, and then here you get 3 times a -4 is -12, that adds to 0. And then the 3-3 entry here, third row, third column, third row here by third column here, that would be -6 times -1 is positive 6. 2 times a -1 would be a -2, so 6 minus 2 is 4, and 3 times a -1 is -3. 4 minus 3, sure enough, is 1. Okay, we've done half of the check. The other half, and just for convenience purpose, I'm going to write A again here, and A is 1 minus 1, 0, 1, 0, minus 1, and -6, 2, 3. The reason I wrote that is we're now going to do A inverse times A. And of course this will be a 3 by 3, because those are all both 3 by 3s. So this will have 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, now let's the 1 entry here, first row, first column, be first row of A inverse times first column of A. -2 times 1 is -2, minus 3 times 1 is -3, so -2 and -3 is -5, and -1 times -6 is +6, -5 plus 6, sure enough, is 1. The 1-2 entry here will be first row here, second column here, that would be a +2 plus 0, that would be a +2, minus 2, that's a 0. 1, 3 entry here, first row here, third column there. 2 times 0 is 0, negative 2 times 0. Negative 3 times negative 1 is positive 3, and negative 1 times 3 is negative 3. Those add to 0. Okay? The 2, 1 entry here, second row here, first column here. Negative 3 times 1 is negative 3. Negative 3 times 1 is negative 3. That would be a negative 6. And negative 1 times negative 6 is positive 6. That adds to 0. 2, 2 entry here, second row, second column. Negative 3 times negative 1 is positive 3 plus 0 minus 2. That sure enough is a 1. The 2, 3 entry here, second row, third column, that would be a 0. Negative 3 times 0 is 0. Negative 3 times negative 1 is positive 3. Negative 1 times positive 3 is negative 3. Plus 3 minus 3 is 0. 3, 1 entry here, third row, first column, third row here, first column there. That's a minus 2, minus 4, that's minus 6, plus 6, 0. 3, 2 entry here, third row, second column, positive 2 plus 0, minus 2, sure enough is 0, and third row, third column, 3, 3 entry, 0 plus 4 minus 3 is 1. Yep, it checks both ways. Not only did our procedure work correctly that we did last time, but checking it, the A times A inverse is the identity matrix, yes, and A inverse times A is the identity matrix, yes. So we have verified that those are inverses of each other. Okay? Now, if a matrix doesn't have an inverse, what do we call it? Anyone remember? There's two names for it. One, of course, is non-invertible, meaning it doesn't have an inverse. But the second one is singular. Okay? And that's what we're going to do now. They claim that this A here may be a singular matrix. 1, 2, 0, 3, minus 1, 2, negative 2, 3, negative 2. Now, if indeed that is, well, if we're trying to find if it does have an inverse, what we do is augment that matrix with the identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. And now start our row reduction. Well, we got a 1 right here where we want it. I'm happy for that. We want this to be a 0. How do we get that to be a 0? Excuse me. I'm so sorry. When I was waiting for students to show up, I was munching on a few almonds and I think I swallowed something wrong. Sorry about that. So how we get this? Yeah, where is it now? There it is. We got a 1 here. We want that to be a 0. How do we make that a 0? Minus 3 times row 1 and add it to row 2. Okay? Okay, we're using row 1, so write it down. 1, 2, 0, 1, 0, 0. The whole row. Okay, do what it says. Minus 3 times row 1 plus row 2. Minus 3 times 1 is minus 3 plus 3. Sure enough is 0. That's what we wanted. Minus 3 times 2 is minus 6. Minus 1 is minus 7. That doesn't look very promising. Minus 3 times 0 is 0 plus 2 is 2. Minus 3 times 1 is minus 3 plus 0 is minus 3. And minus 3 times 0 is indeed 0 plus 1 is 1. And minus 3 times 0 is 0 plus 0 is 0. There's the new second row. Next we want this negative 2 to be a 1. How do we make that happen? 2 times row 1 plus row 3. And that will make that to be a 0. So 2 times 1 is 2, minus 2 is 0. Sure enough, that did. 2 times 2 is 4, plus 3 is 7. Interesting. Okay. 2 times 0 is 0, plus a minus 2 is a minus 2. Oh, interesting again. 2 times 1 is 2, plus 0 is 2. Okay, I think I did that right. 2 times 0 is 0 plus 0 is 0. And 2 times 0 is 0 plus 1 is 1. All right. I hope you see what's going to happen. Let's not mess around with dividing by negative 7, row 2, or row 3 by positive 7. Let's just add row 2 and row 3. Okay. Leaving row 1 alone, there'll be a 1, 2, 0. It doesn't really matter what it is. 1, 0, 0. Okay. And we'll leave row 2 alone for now. 0, negative. This isn't the way we'd normally do it, but I'm going to do it this way. Negative 7, 2, negative 3, 1, 0. Adding row 2 and row 3, 0 plus 0 is 0. Minus 7 plus 7 is 0. And 2 minus 2 is 0. And then this will be a minus 1. This will be a 1. And that will be a 1. It doesn't matter what that is. You are not going to get an identity matrix here. You can't get it with a 0 being there. There's no way you can make that a 1. So this is non-invertible or singular. Means the same thing. Yeah, it almost sounds like someone's knocking, but maybe, I don't know. Excuse me just a minute. I'm going to pause the recording just in case someone's at the door. My wife's at work today, so false alarm. But with her not being here, I didn't want someone to be standing out there knocking at the door. Okay. So any questions on that? Let's just see how the book did it. They got down to the same point and had 0, 0, 0, negative 1, 1, 1. And indeed, that's no way you can get that to be in the left 3 columns will never form an identity matrix now. No matter what you do to them, you're not going to get that 0 to become a 1 at all. Okay, so that's a singular matrix, meaning it does not have an inverse. Now, the next chapter, we're going to talk about something called a determinant. Okay? And jumping a little bit ahead, you can use Gauss-Jordan elimination, which is what we were doing here, to find the inverse of a matrix. It works well, even as a computer technique. It works quite nicely for matrices of size 3 by 3 or greater. However, for a 2 by 2 matrix, there is a much easier way you can do it. Okay? Now, I'm going to show you now what they do in the book. Here A is a 2 by 2 matrix. Okay? And we're going to leave it in letters and make it general. Now, by the way, James didn't show up. Oh, no. No, just the two of you and me. Okay. Here's matrix A, B, C, D. This is very generic. Okay? So it can't be it just worked because you use those numbers. If you were trying to row reduce this, the first thing you would do would be to, well, I'm not going through it all, but here is the deal. Here's the rule. This is invertible if the following is true. AD, the cross product this way, minus BC, I want to make sure I wrote it the same way they did, minus BC, which is the upper cross product, if that result is not equal to 0, this is invertible. Okay? If it is equal to 0, it's not. Okay? Now that wouldn't work on that 3 by 3 that we just did, because that's a lot more involved than that. But for a 2 by 2, that's how we check. Okay? If that cross product, AB minus BC or CB, it doesn't matter how you say that. If that is not equal to 0, it's an invertible matrix. If it is equal to 0, not invertible. Okay? Now, what is the inverse then? This tells you is invertible. What's the inverse? Well, A inverse would then be, okay, 1 over, and by the way, this is called the determinant. Okay? AD minus BC that's why it can't be 0. Okay? And then this is the strange part. Okay? You reverse the main diagonal elements, make this your D and this your A, and then negate your anti-diagonal. Make that a minus C and a minus B. That will give you your inverse just like that. Okay? Now, we'll talk more about determinants next chapter, chapter 3. Okay? They're pretty easy, they're sort of fun. Let's go. I think I'm going to need to clear the screen now. Any questions before we go? All right. It says, if possible, find the inverse of each matrix. Well, here's matrix A. 2 by 2. Remember, to have an inverse, a matrix has to be square. 3, negative 1, negative 2, 2. Okay? Let's see first if it has an inverse. What is the cross product here? That's a 6. And then minus a 2, that's 4. That's not 0, so it does have an inverse. What is the inverse then? See, that was so easy to do. The inverse would be 1 over 4. See, you calculated, but use it now. And then we're going to do our change here. Swap the main diagonals to 3 and negate the others. 1, 2. Okay? So that would be 1/4 of 2 would be 1/2. 1/4. 1/2. 3/4. And frankly, I'd just as soon leave it in that form. Okay? How can we check this? Well, let's do the product. Let's do 3 minus 1, negative 2, 2, times, now I'm going to put the 1/4 out front. Remember, you can do that. And that would be 2, 1, 2, 3. That's what we found the inverse to be. Okay? So let's multiply and see. That would be 1/4 of a 2 by 2 matrix. First row, first column, be first row here, first column there. 3 times 2 is 6, minus 2 is 4. That's looking good. First row, second column would be first row here, second column here. 3 minus 3, 0. 2, 1 entry here, second row, first column. Minus 4 plus 4, 0. And 2, 2 entry would be second row, second column. Minus 2 plus 6 is 4. And 1/4 of that would be 1, 0, 0, 1. Yep. Now, if you want to, you can reverse them and do them again. Frankly, if it does produce the identity matrix, basically one will do. Okay, but you can reverse the order and do 2, 1, 3, 2, 2, 3 times 3, negative 1, negative 2, 2, and see what works there. I think you'll find it comes out the same. All right, let's do the B part. Here's matrix B, and matrix B here is 3, negative 1, negative 6, 2. Okay, do the cross product. 3 times 2, that's 6, minus negative 6 times 1, negative 6 times negative 1, and that would be 6 minus 6, 0. Not invertible. Singular. Okay? Can't happen. The determinant is 0. Now, this is jumping too much ahead, but with a 2 by 2 matrix, it's almost easy to tell. If one row is a multiple of another row, it's not going to be invertible. And you see the second row here is minus 2 times the first row. So, also works with columns. The first column is minus 3 times the second column. Okay, so it doesn't work. Okay, so it's a non-invertible matrix. So that being said, any questions before we clear this? Okay, now let's look at some properties of inverses. Now here's where I wonder if it's better for me to type them or write them. The thing is, there's a lot of superscripts and subscripts. I don't see any subscripts, but there are superscripts. So maybe it's better for me to write these. Okay, because I know you can't see your ebook and watch the Zoom at the same time, or I don't think you can. But let's see what we've got. Here's what's given. A is an invertible matrix. What does that mean? It means that A has to be square. And not only square, but it does have an inverse. Okay? Now, second, K is any positive integer. K is a positive integer. Okay? C is any real number, a non-zero scalar. Any number. It doesn't have to be an integer, any number, it just can't be zero. Then, if that's given, those are the givens here. Okay. Here is what we get out of it. A inverse certainly exists because A is invertible. Okay. A raised to the kth power exists. You can just multiply A by A by A by A is up to K times. Okay. CA, that's the arbitrary constant multiplied by A. Okay. And A transpose. Remember A transpose? Reverse the rows and orders, the rows and columns of A. Okay? If this is invertible, then all these are also invertible. Okay? Now, and the following statements are true. First statement, and this is hopefully pretty obvious. The A inverse, which is the inverse of A, it does exist because A is invertible. But if you take the inverse of that, you wind up back with A again, which sort of makes sense. If one's the inverse of the other is the inverse of that. So there's the first one. The second one, okay? If you do A to the K, okay, we know that's invertible. We were told that up here. So if you take this and look for the inverse, here's what you can say about that. That's also A inverse raised to the kth power. Hadn't thought about that, but it indeed would be true. Okay? Now, number 3. If you take that constant C, scalar, non-zero, times A, that's invertible matrix. So what is its inverse? Now here's sort of an interesting thing. It's the multiplicative inverse of C, 1 over C, times, let's just do it, A inverse. Okay? 1 over C times A inverse. And then the fourth one. If you have the transpose of A, and we've already said it's invertible, so you can take its inverse, and if you do that, it happens to come up being A inverse, guess what? Transposed. And that is indeed the case. Now they do have a little proof here, and it takes several lines, so I'll let you work through the proof if you're interested. But notice here, the interesting thing is the inverse notation and then your power notation, you can flip them around. Okay, and they mean different things, but you can flip them around. Like right here, A to the K inverse is A to the inverse to the K. And A transpose inverse is A inverse transpose, even though they mean very different things. Now this one is sort of interesting too. The other way you could write that is because C is a scalar, this is C to the minus 1. A number to the minus 1 is a reciprocal times A to the minus 1. Now, I think the reason they don't write it that way, they don't want you confusing this. For a number, c to the minus 1 means 1 over c. For a matrix, a to the minus 1 does not mean 1 over a. We don't even know what that means. It means the inverse, but the symbols work. All right. There is a little discovery at the bottom of page 67. Okay. So let's do that little discovery. I can't remember if this is a bad one or not. Let's see. I don't think we quite did this. I'm going to go on and do this one too. It's a lot like this one. It's a to the minus k. Now that is a strange expression, because a number to the minus k means put it over that number to the k. That's not what this means, okay? But what that does mean, it's the same as this. It's a to the minus 1 times a to the minus 1 times a to the minus 1. It's the same as these two. So you could actually put another equal sign, and all three of those are the same. This is just a really weird way to express it, but it means the same thing as both of those. Okay? Now, and then just a little reminder that a to the jth, where j is a positive integer, times a to the kth, where k is a positive integer as well, is equal to, keep the base, add the exponents, j plus k. That worked for numbers. It also works for matrices. Okay? And another one, if you had a to the jth raised to the kth power, that's the same as a to the j times k, just like it is for numbers. True for any integers, j and k. Now they say integers, they've quit saying positive integers, because this thing basically says you can make it work for negative integers as well. All right, that done. Let's clear the screen, unless you have a question about it. Any? Okay, we'll clear the drawing here. And I don't know, did we just lose Jesus? Yeah, it looks like we lost Jesus. I don't know, hopefully he'll be back. Okay, so here's a discovery. A is equal to 1213. Okay, now based on what I said before, it's a 2 by 2. You can look at that and say, yes, that's invertible. I don't know if you recall that, but you can. Here's B. B is 2, -1, 1, -1. And I can look at that and say, yes, that's invertible. Remember I said for a 2 by 2 to be non-invertible, one row or one column has to be a multiple of the other. Neither of these are. Now, what it asks us to do is find AB inverse. So the first thing we got to do is find out what AB is. Well, AB is going to be a 2 by 2 matrix, right? And when we multiply it together, first row, first column, that's first row here times first column here, that would be 2 plus 2 is 4. First row, second column, be first row, second column here, -1 minus 2 is -3. Okay, 2, 1 entry, second row, first column here, 2 plus 3 is 5. 2 entry here, second row, second column, is -1 minus 3 is -4. Excuse me just a moment. My throat is getting incredibly dry. I've been talking since 8:30 this morning. And I'm out of water. Sorry. Let me get a swig of Coke. Okay. So there's AB. Now they ask for what's AB inverse. Now if you recall, AB inverse of a 2 by 2 matrix is, let's do the determinant. That's a -16 minus a minus, which is +15. So the determinant is 1. So the inverse of AB, yeah, that's what they're asking for, is equal to 1 over -1, which is minus, and then we swap these two, make a -4 here and a +4 here, and then negate these two, making a 3 here and a -5 here. Okay, so we found AB inverse. Now, the next thing it said is find A inverse times B inverse. Well, let's do A inverse first. Okay, to do A inverse, we need to find the determinant. 3 minus 2 is 1. Okay, so that would be 1. And by the way, I'm going to change this to read, negating that would be 4, -3, 5, -4, which, interestingly enough, is the same as AB. Whoa, whoa. Now that may be just happenstance here, but in case that is. Okay, so A inverse, the determinant is 1, and then we'll reverse these two, 3, 1, and -1, -2. Negate the other two. All right, B inverse, okay, the determinant here is -2 minus a minus, which is +1. So that's going to be a -1. So I'm going to just put a minus sign here, and then we'll reverse these two, make it -1, 2, 1, and negate these two, -1. Okay, and now negate or carry that through, make it a 1, -1, 1, -2. Okay, now that's A inverse and B inverse. Now what we want to do is multiply these two together, this one times that one. So A inverse times B inverse is, okay, it's a 2 by 2, and first row, first column here, that would be a 3 minus 2 is 1. Second row, first row, second column, now I can't read my right, that's a minus. So that's a -3 plus 4, that's a 1. And second row, first column, -1 plus 1 is 0. And second row, second column is 1 minus 2 is -1. Okay, I hope I did that right. Now what we're going to do, I'm going to write A inverse again over here. Just copy it down. 3, negative 2, negative 1, 1. And I'm going to multiply these two together. Okay, that will also form, this is B inverse, A inverse. That's going to be a 2 by 2. The first entry will be 3 plus 1 is 4. Negative 2 minus 1 is minus 3. 3 plus 2 is 5. And negative 2 minus 2 is minus 4. Uh-oh, look at that. That's the same as AB inverse is the same as B inverse times A inverse. Not the same as A inverse B inverse, but it is the same as A inverse as B inverse A inverse. Okay. All right. And you can go to larsonlinearalgebra.com for an interactive version of that type of an exercise that we just did. Okay, how are we doing? We got about 17 minutes, I think. So let's do example 6. I think we're going to need to clear the screen. All right. It says compute a to the minus 2 in 2 different ways and show the results are equal. Let's first do A. A is 1, 1, 2, 4. By the way, it is invertible. We know that. Okay. Now, 2 ways we can do this. One way is to find the inverse of A and then multiply that by itself. Okay. The second way is multiply A by itself and then find its inverse. So let's first do the first, A inverse, and because this is a 2 by 2 and it is invertible, let's do the determinant. That would be a 4 minus 2 is 2, so it would be 1/2, and then we reverse the main diagonal for 1 and negate the others, minus 1, minus 2. Okay, now we're going to take that and multiply it by itself. Okay, so that would be multiplying by another 1/2, which is basically going to make that a 1/4. And then we'll multiply that by 4, negative 1, negative 2, 1. Okay, so this is going to be, so now this will be this thing squared, okay, which is going to be a manifestation of that. Okay, so it'll be 1/4 of, okay, this will be a 2 by 2 matrix. 4 times 4 is 16, plus 2 is 18. 4 times minus 1 is minus 4, minus 1 is minus 5. This is minus 8, minus 2 is minus 10. And this will be minus 2 plus 1 is minus 1, I think. Oh, goodness, I'm getting dizzy. I think that means I'm getting hungry. Okay. Sorry, I'm out of water, but stave off the hunger a little bit. So that is one rendition of a to the minus 2. The other is to take a and multiply it by itself. Okay, a times a, and that will be 1 1 1 2, no 2 4, I can't write, times 1 1 2 4. And before it makes me make a big mistake, let's write this as 2 4. Multiply those together and you get a 2 by 2. 1 1 entry will be 1 plus 2 is 3. 1 plus 4 is 5. 2 plus 8 is 10. 2 plus 16 is 18. Okay. Now we want to take the inverse of that. So let's first multiply here. These have gotten to be some pretty big numbers here. That's a 54, I think it is, minus 50. That sure enough is 4. So its inverse would be let's just call it a squared inverse is going to be 1/4 because it's 1 over that determinant. And then let's do the determinant of this and we'll reverse the thing. 18 3, oops, I messed up something here. Minus 5 minus 10. Okay, 3 of those are right. 1 of them is not. Let's go back and check this again. The 2 2 entry here. Plus 2 plus 1, that's a 3. I don't know how I got that. So sure enough, these two are indeed equal. A to the minus 2 calculated this way, a inverse raised to the second power multiplied by itself gives you that. And a times itself, a squared, taking the inverse of that, gives you that too. And these are indeed equal to each other. Okay. So that was example 6. Now they went on and multiplied through by the 1/4. I found it easier to leave the 1/4 on the outside, but either way you want to do it, it's fine. All right. Let's summarize that with this theorem. Theorem 2.9. If A if A and B are both invertible matrices, if you haven't gathered it now, when I say I and V, that means they're invertible, of order n, in other words, they're the same size, then if that's true, they're both invertible, they're both the same size, then the product of AB is also an invertible matrix. Okay? And not just I'm sorry, and not just that, but its inverse, we know it's invertible, so its inverse, AB inverse, is equal to, and this is what the discovery showed us, B inverse times A inverse. Okay. in that order. Okay, so there was theorem 2.9. They do a little proof here, and it's a pretty decent little proof. Goodness gracious. And basically that proof would be this. Let's see, are they doing to show that that is indeed, that this right here, if I could get my pen to show up somewhere, that this right here is the inverse of that. Okay? Then here's how you do that. Okay? Let's take AB and multiply it by B inverse A inverse. And what does a matrix times its inverse give you? The identity matrix. Well, let's see if that's true. Well, this is A times B inverse, and remember they're both invertible matrices, times A inverse. Okay, well, this is the identity matrix. Okay, so that'd be A times I times A inverse. Now this is the same size n. Okay, but A times I is just A times A inverse. A times A inverse is I sub n. Okay, so there you have it. These must be inverses of each other because their product is the identity matrix of that dimension. Okay, that was a fairly easy little proof to do, so I went on and did that one. Okay, now if you generalize that, you can also say this. What if you have a whole string of matrices that are all invertible matrices? Okay, so you got A1, which is an invertible matrix, times A2, which is an invertible matrix, times A3, which is an invertible matrix, and dot dot that all the way up to and include A sub n. You have n of these invertible matrices, and you're multiplying together. Well, what's their inverse? Well, the theorem, if you expand it, would say that's A n inverse times A n minus 1 inverse times A n minus 2 inverse dot 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 down to A sub 3 inverse A sub 2 inverse times A sub 1 inverse. Okay, and that sure enough is true. Okay, and you can see example 4 in the appendix, and that will carry that one. Now 5 minutes, let's see if we can do example 7. So I think we'll come up and clear this and do example 7. Find AB inverse. This is what we're looking for. AB inverse. Okay, for these two matrices. Here's matrix A is equal to 133, 143, 134. A 3 by 3 matrix. Here's matrix B, another 3 by 3 matrix, good for it. 1, 2, 3, 1, 3, 3, 2, 4, 3. Okay. Now, thank you very much. They say using the fact that A inverse, thank you for not making me do this, is 7, negative 3, negative 3, negative 1, 1, 0, negative 1, 0, 1. And that B inverse is equal to 1, negative 2, 1, negative 1, 1, 0, and 2/3, 0, negative 1/3. Okay. Wow. Almost took me 3 minutes just to write that down. Okay. Now we want to find AB inverse, knowing that A inverse is that, B inverse is that. Well, basically all we have to do is multiply. To get this, we do B inverse, A inverse. So we multiply that. So I'm going to take the A inverse and write it again over here. 7 minus 3 minus 3, negative 1, 1, 0, and 1, negative 1, 0, 1. Okay, and we're going to multiply those two together. Okay, and this will give you that. It's going to be a blank, 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 blank. Okay. First row, first column. 7 plus 2 is 9, minus 1 is 8. Second, negative 3 minus 2 would be negative 5. That's a negative 5. Third, minus 3, 0, plus 1 is a minus 2. Okay, 2, 1 would be minus 7, plus 1 would be minus 6. That's a minus 6. 2, 2. I can't read my writing. I hope both of those are 1s. Yeah. No, the first one's a minus 1, yeah. So that's a 3 plus 1 is 4. So that's a 4. And the next one is 3 plus 0 plus 0. That's just a 3. Next one is 14 thirds plus 1 is 15 thirds. That's going to be a 5. Minus 2 plus 0 plus 0 is minus 2. And minus 2 plus 0 minus 1/3 is minus 7/3. That seems bizarre. Let's see if that's it. I was doing it really fast in my head. Let's see. 8, negative 5, negative 2, negative 8. Ooh, missed that one. 4, 3, 5, negative 2, negative 7/3. So this one right here I kind of botched. That would be minus 7. Ooh. Minus 1. No. This is just ugly. It's minus 7 minus 1 is minus 8. Yeah, it's a minus 8. I'm sorry. Minus 8. Okay. Yep, we got it right after a mistake. All right, I think that's gone over. So we'll pick up next time. Any questions so far? Okay. Yes.
I said no question.
Oh, no more questions. Okay. We'll pick up next time with example 10. Okay. Theorem 210. Okay. Let's see how many homework exercises we were able to. Oh, we're so close to finishing. I think you can do any of the odds 1 through 5. You can do any of the odds 7 through 29. Now they suggest you use a graphing utility or something like that, computer or something on 27 and 29, but you might be able to do it without them. Do any of the odds 31 to 35. And by the way, all these are at calcchat.com. Either 37 or 39. And either 41 or 43. And stop there, because we haven't gotten to solving systems yet. That will come next. So stop there, and that will get you plenty to do until Thursday. Any questions? Other questions? All right. Are we down just to you? I guess so. Yeah.
I emailed you, but you haven't answered. That's about it.
Okay. What was your email?
About the writings, the essays.
Right.
So we're gonna find the information I need on Blackboard under what?
Okay. You mean for the instructions for writing the paper?
Yes.
Okay. Go to week 1 in Blackboard. Okay, you know what I'm talking about? Go to this course, week 1. The first thing is, the overview, blah, blah, blah. The second tab under that says instructional materials. Okay, under week 1, instructional materials. Okay, and then you'll see at the top it says PowerPoint. There aren't any PowerPoints. The next it says, I think something like recorded lectures, and it tells you about the YouTube videos. Now, don't forget that. We're coming back to that in a minute. The next says instructional videos, and there I put a bunch of videos from other sources that I had either gotten, found, or other students had given me. But then the next thing says handouts, and under handouts there's 2 things listed there. One of them says research paper instructions, so you can go there and read the research paper instructions. Okay, that's under week 1, instructional materials, handouts. Now go back up to that previous thing that was the YouTube videos. Okay, that was like the second thing listed there. Okay, under YouTube videos, if you go now, if you remember, the first of this term, we couldn't record lectures because they had failed to pay the bill, and so we couldn't use Screencast-O-Matic. But last summer I taught this course, and there under that first day of class, which I think it says syllabus, and that's still out there under YouTube videos, but it'll be near the top, not near the bottom. And go to that one, and I believe that one will have a full rendition of me talking about what's required in the paper. So you got 2 places to go to. You can read it under handouts under week 1, or you can hear me talk about it under recorded videos under week 1. But both those places you can find that. Does that answer well enough? Hello? Yes. Okay. And it's the same true in all 3 classes you're taking. You'll find those same things there, just like that.
The same as during the summer?
Yeah. Same as during the summer. Yeah.
Okay. Thank you.
All right, Shirley. Any other questions? Great question, by the way. Okay, if no more questions, I'm going to stop sharing, and I will also end the recording. So take care. We'll see y'all tomorrow, right? Good deal. Twice. See you then. Bye-bye.